My topic is extraterrestrial drilling. How on earth can Martian drilling help us? Now, how many of you have seen the movie Armageddon? Okay, quite a few of you. For those of you that haven't seen it, Bruce Willis is a drilling engineer. He's an action hero, but he's a drilling engineer in this movie. And it turns out there's this asteroid the size of Texas coming toward the Earth. And so he and a bunch of rejected roughnecks from other places fly up to this asteroid, drill a hole on it, set off a nuclear weapon, splitting the asteroid in half. If that's where you think you get your knowledge about extraterrestrial drilling from, let me tell you, everything in that movie is wrong. Everything is wrong, except for one thing. They got one thing right. You know what the one thing was? It was a drilling engineer that saved the world. The only thing they got right. Well, you know, sometimes when we stand around and we start thinking about the great philosophical questions of our time, one of the most intriguing and most earth-shattering type of question you might want to ask is, are we alone in the universe? Are we it? And so you might be thinking to yourself, wait a minute, this is the Society of Petroleum Engineers, and this is the petroleum engineering profession. What has that got to do with answering the question, are we alone in the universe? And the answer is, you bet it does. It has everything to do with it. And if you'll give me the next 40 or 45 minutes, I'll explain. And so it starts off with life. We need to figure out, where is it? Right now we know of one instance right here, right? Us. We are life. But you know, where else is there that could possibly have harbored life so we can answer that question, are we alone in this universe? Well, the most accessible place that we think that would have that possibility is Mars. Why? Because it's a smaller planet. And the thought was that because it's a smaller planet, it would have cooled off faster. And if it cooled off faster, perhaps the conditions that allow life to begin got its start there. Perhaps there was a second start of life on Mars. But because it maybe have started faster than it did here on Earth, could it have been that it actually got started on Mars, and due to the low escape velocity of Mars, the planet of Mars, if something had hit it and blasted rocks off, could those rocks have actually harbored life that was being created there and then actually made its way to the Earth and seeded the Earth's ocean? Was there one start, but it was on Mars and migrated to Earth? Are we in fact Martians? And so that's the kind of question we're trying to answer here. And let's talk about Mars. What I want to do is I want to kind of give you a little setting of what Mars is all about. And if you take a look at my physical data here, a couple things kind of point out here. One, if you notice, the mass is about 10 times as great for Earth as it is for Mars. It's we're a much more massive planet. And obviously it's because our diameter is twice as big. That means that the gravitational field on Mars is only about 40% that of Earth. So if you weighed 100 kilograms here, you'd be only 40 kilograms there. So a great place for a diving. The escape velocity, as I already alluded to, is 11,200 meters per second here, whereas on Mars it's less than half that at 5,000 meters per second. We're also, if you notice, if you use one astronomical unit, the distance from the Sun to the Earth, Mars is 50% further away. And of course, we know about the inverse square law of light. And then the day is about the same, but the year's twice as long. And let me tell you, it gets darn chilly on Mars. Now, it's kind of an interesting little tidbit here, and that is, if you took all of the land on the Earth, all of the land surface area on Earth, you know, North America, Europe, Asia, South America, Africa, Australia, Antarctica, added them all together, you'd have roughly what the surface area of Mars is. So think about that. It's what you're trying to infer about the planet from little bitty landers would be like a lander landing here in Aberdeen and another one landing in Denver and trying to figure out how the planet's put together. In essence, that's what we're doing. Just as a little technical aside, I find this interesting, that the land area of Africa is about the same as the total surface area of the moon. So when you start exploring the moon, we're exploring something about the size of Africa. So kind of puts it in perspective. Now, I love this picture. This picture's got some really cool stuff. This is a topographic map of Mars, and it's set at some arbitrary sea level of 0. And let me point out some of the salient points on this. Right there is called the Hellas Impact Basin. Basically, that's as big a smack as you can have in a planet without actually splitting it in half. If you notice, this thing is about 8 kilometers deep relative to whatever that arbitrary sea level is. It's rather massive, and if you notice, there's a lot of cratering all around it as if it were blasted out and came out. What was kind of interesting is the very first Mariner spacecraft to fly by and take a picture, they took like 9 photographs of Mars, and it went something like this. And what it saw was a bunch of craters. And it went, uh-oh, this place looks like the moon. Therefore, it must be dead. Well, they said, well, we need, 9 pictures is not enough. Let's go ahead and get some more. So they sent Mariner 9. Mariner 9 was the first orbiting spacecraft around Mars. And it got there just in the middle of a huge dust storm, and all they saw were 4 white dots. And as the month, and then the second month went by, the dust sort of settled, and there was Mars in all its glory. It was amazing what was found. For example, this right here, this is called the Tharsis Bulge, and it's an area that has what looks like a upwelling here, and then what looks like a canyon. And in fact, that's the Canyon of the Mariner, or Valles Marineris. And it is 4,000 kilometers long, and it's about 7 kilometers deep and 200 kilometers wide. That is a monster canyon. In fact, it's the largest canyon in the solar system. And it looks like, if you look at it, it looks like something kind of came out and went into this big blue area right here that looks fairly flat. That area is fairly flat. And then if you notice over here, those are those 4 white dots I was talking about. It turns out those are volcanoes. It turns out that Mars, because it cooled off so fast, it originally had some continental drift going on, but that the core kind of froze out and it stopped. And the net result was that if a volcano started up, it just keeps going in the same place for how many ever billion years. And when you do that, you can make a big volcano. This right here is Nix Olympium, and it is 22 kilometers high and has a radius of roughly 300 kilometers. If you want to compare that to the state of Arizona in the United States, that's roughly what the surface area of the base of that is. It is a huge volcano and is considered one of the largest, if not the largest volcano in the solar system. And so if you kind of compare that, that's almost like from the bottom of Mauna Kea in Hawaii, in the bottom of the ocean, all the way to the top of that particular shield volcano. It's along the same order. It is a monster volcano. We haven't done real well. We've sent stuff there and we've had some monumental mistakes. Right now the score is Mars 24, Earth 15. And we have had a lot of failures. I know this country right here had its own failure with the Beagle. And of course we had some spectacular failures when we forgot to convert from the English system to the metric system. And so there's been some interesting problems that have arisen, but you know what? We have had some success. And one of the very first landers was the Viking Lander in 1976. The Viking Lander was specifically designed to answer the question, are we alone in the universe? Is there life on Mars? It had 4 experiments on board. And the 4 experiments were to test. They took a little scoop, put a little soil in there, and they tested it, and the answer was ambiguous. There was some reason to think that yes, it was. There was some reason to think no, it wasn't. There could have been some inorganic chemistry going on. It could have been organic chemistry. Oh man, nobody knew. And so the net result was that this guy right here was just gave us an answer we just couldn't answer. You know, one of the problems though with Viking is that you notice there's no wheels. It just stays put. It can't go anywhere. So once it lands, it's there forever. In fact, still there. So the folks at NASA said, we need mobility. And so what they said was, let's build a device to see what we can do. And so they built the Sojourner Truth. If you notice there, the chassis on this with the wheels and so forth looks very common to all spacecraft that are used for mobility today. In fact, that was the first test fixture. That little guy right there was about the size of that. And it was an internet sensation. People just loved it. It's like, oh, look at that little thing. And so it was one of those kind of devices that was designed for about 90 days. And it drove around. They were testing the driving procedure and all. It was not designed to find the answer. It was designed to prove an engineering concept. The landing procedures, the getting off of it, and being able to drive around and do some tests. Once they got that kind of worked out, they said, let's upsize it. And so they developed the Spirit and the Opportunity, which landed in 2004. The Spirit and the Opportunity are about the size of that table right there. And so it's a fairly decent sized thing. It's a solar powered unit. And what's kind of interesting about it is this little device right there. Keep that in mind as we go forward. The Spirit was in Gusov Crater. They landed it in this crater with the idea of being able to see if there was indeed water at one time. And so it was driving around. Unfortunately, one of the wheels went bad. They had to turn it backwards. They were driving it backwards. It got caught in a sand dune. Unfortunately, it kind of got tilted in the wrong direction so that the solar panels wouldn't pick up the sun. And the net result was, over the winter, it froze to death. And so it is no longer with us. May it rest in peace. However, the Opportunity was in the Meridiana Plains. And to this day, it's still driving along. It's done about 23 kilometers worth of driving in 10 years. So you think your traffic's bad? But it has done some remarkable science along the way. And so this thing is still going to this day, the Opportunity. Now, because of all the mistakes that have been made and crashes and whatnot, they had a lot of leftover parts. And they're like, well, we've got all this flight-tested leftover parts. Let's build another spacecraft, and we'll call it the Phoenix, because it's rising up out of the ashes of the last stuff. And its job was to land on the pole. It was not designed to last a long time. All it was designed to do was look at what was under the soils of the pole. They were looking for ice. What kind of ice? And so forth. And so that's what this guy was all about. And it had a little scoop on it, just similar to what the Viking had, to be able to collect some soils. Those of us from the U.S., we're always looking for bigger, right? And so we made it bigger. This right here is the Curiosity, and what has to be the first interplanetary selfie I've ever seen. And this particular device right here is the size of a sport utility vehicle that you might be driving around wherever it might be. And this one's got actually a nuclear power source right there. It's got this what called mass cam and so forth. It's you notice the chassis looks just like all the other chassis, a very common procedure. But this guy right here is what I want you to pay attention to, again, as we go forward. The Curiosity landed in an area that they're looking for, what is the geology like and all that. Why? What is the one thing that we know that everything we know about life has associated with it? What's that one chemical? Water, exactly. Water, H2O. Water. Water has everything to do with life. We've never found life as we know it that wasn't associated with water. So that's what they're doing. They're looking for water. Let's see if we can find some evidence of that. This happens to be the Ravi Vallis, and if you notice, this area right here has some sort of what looks like an upwelling of fluids, and it looks like a catastrophic time of flood of some kind of liquid coming out and flowing on the surface of Mars. This was probably on the order of 3 or 4 billion years ago when this happened. This particular catastrophic flood would have probably been about 5-6 weeks in duration. And just to put this in scale, that's about 400 kilometers. That is a huge biblical-sized flood. In fact, I did some calculations and came up with you would have about 19 trillion, 10 to the 12th power, barrels of fluid a day. That's the kind of flood that is right there. So that is a remarkable flood, but the problem is it was just, just momentary in the life of the planet. What you really need is, if you're going to have life, you need it to last and be there for a while. And that's what the Curiosity found when it went through this little valley on its way to what they call the Scott Hills. This valley right here, if you look at that, as it went through there, you can almost see where it looks like water has flowed for some time frame and basically created these nice flat layers of sediment. And so if you take a look at that, that looks like water. In fact, some of the chemical evidence indicates it might have been fresh water. And so it's another visual possible that water was on Mars at one time, and it lasted a while. That was a long time ago, though. Is there any evidence that it's still there? Well, if you take a look right here, this is what we call the Gorgonian crater area, and you notice that it looks like some sort of flow coming down and forming an alluvial fan. You can kind of put the scale there at 400 meters, not real big. But we say this is recent because if you look at it, one of the ways you tell the age of a planetary surface is count the craters, right? Because you can imagine that cratering is going to happen like maybe once every X number of years or whatever. And so all you got to do is count the craters, and you end up with how many years it's been around. Do you see any craters? There's no craters. So the evidence is that has to be a relatively recent, and geologically speaking, time frame. Right? In a relatively recent geologic time frame, it looks like some sort of liquid flowed out of the planet and created that alluvial fan. Back in I think it was 87, there was an exciting announcement from the Lunar and Planetary Institute out of Houston, Texas. We found life. Well, how did they do that? Well, this happens to be the famous Allen Hills 84,001 meteorite. 84 for 1984 is when they discovered it. Allen Hills is in Antarctica, and it was the first one they found. And what they said was, look, we sliced it open, we sampled the isotopes and the gases that were trapped in there. It turns out they are had the identical signature as the Martian atmosphere does. Ergo, this must be from Mars. And so the thought is, if this is from Mars, and we open it up and we see this, could that be a fossil bacteria? That's what the interpretation was. But unfortunately, there are other inorganic possibilities that may have created this. In addition, one thing that I think is kind of tough on it is that the distance from here to here is only about 1/10 of the smallest virus that we know about. The answer, again, ambiguous. We don't have a definitive solution. So the question is then, water. Was there water on the Martian past? We've got evidence of ancient water. You've got the Valles Marineris and what that looks like. You've got all of the different types of flow channels that look like are going on, and even today. So the question is, could this have been Mars in the past? You know that big blue area I pointed out on the topographic map? Could that have been an ocean bottom? Could that have been the bottom of an ocean where the Valles Marineris area was basically flowing into this giant ocean the size of the Atlantic and about the same volume as the Atlantic? And I just flew over that thing, and that's a big ocean, y'all. And so there's a lot of water. And in 4 billion years that it's been around, it hasn't had enough time to evaporate off the planet. It's still got to be there somewhere. Well, that's why they sent the Phoenix. They wanted to see, could it be in the polar caps? The answer is yes, indeed. There was water ice in the polar caps, but it can't be nearly the amount that the evidence is showing. So therefore, where's the rest of it? It has to be in the subsurface. It's not in the surface, that's dry. So it has to be underground. If the water's underground, then that's where we're going to find life, if there is life. And so, what would it look like? Well, it could be absorbed on minerals. We're petroleum engineers. We deal with clay and connate water, right? Could that have water molecules on the clays and so forth? Well, that's a possibility. How about hydrous minerals? We deal with anhydrites and so forth, where it's chemically bound to the rock? Could that be? Or is it just literally liquid, or more than likely ice, because it's a very cold place? Or even a gas hydrate if there was some methane mixing in with the system. And I asked one of the scientists about that, and being a drilling engineer, I get a little nervous about drilling into something that could depressurize and cause a blowout. And I asked the scientists about that, and they're like, well, that would be good. What, a blowout? And it's like, yeah, then we get to see geology in action. Oh, I can just see it now. NASA deflates Mars, size of asteroid, you know. So why is the water important? Well, if you want to find extraterrestrial life, we've got to follow the water. Because everything we know about life has something to do with water. But there's other things that we need to do. If you want to know about the climate of a planet, follow the water. Think about here on Earth. The water coming from the subsurface up into the atmosphere, raining back down and creating all sorts of interesting effects called rain, snow, hurricanes, whatever. Understanding that water cycle will tell us about the climate. How about geology? Any geologists in here? Okay, good. You know how water affects, right? Yeah, right. Water's got some huge effects on geology. Follow the water and you'll learn a lot about your geology. And so, what is that and what is it doing and where did it go? And that's, you know, was there standing water like an ocean in the past? And then finally, resources. If we're going to go to another world, you know, when I think about my suitcase, I know a lot of people complain that I have a big suitcase, but it's like, you know, if I had to carry all my food and everything with me, I'd have like, you know, baggage fees that would be out the wazoo, man. It would be huge. If you could carry it and get it here, well, that makes a lot of sense. So why not do the same when you're exploring other worlds? Find the resources out there. We call it in situ resources. What is one of the best in situ resources? Water. Think about it. I can take water and drink it. I can take water and split it. I can breathe the oxygen. I can recombine the hydrogen and oxygen in a rocket and go home. And so by having water resource, I can actually enable exploration. So what is the motivation for drilling on Mars? One, we really want to understand what is and the distribution of the water, if there is any water under there. We also want to understand the geology and what's going on with the crust of Mars and so forth. Of course, we were looking for those organic molecules so that we can see whether there was past life or even life today. And then finally, we also would like to characterize the geophysical environment. And one of the key things there is the heat flow. We'd like to know how much heat's coming out of the planet so that we know where does the ice turn to liquid. How deep is that in occurrence? And I mentioned this one right here because it turns out they're getting ready to send a probe for that one in about another 2 years. Now this is, believe it or not, from the Oil and Gas Journal. I took that, just made a little snapshot and put it on here. And I've got it broken into what I call reservoir engineering and drilling engineering. Okay, so the reservoir engineers are over here. You know, there's this big dry area where the sun has basically baked out any sort of liquids whatsoever. But then eventually you'll get to where the liquids are below where that heat would be from the sun and the desiccation effect of that. And you might get some ground ice, what we call the cryosphere. And depending upon the heat flow of the planet, eventually that ice will melt and you'll probably get an unsaturated area, then perhaps some sort of saturated zone down deeper. If we're looking for liquid water, that's where you would look for it. Drilling engineering, on the other hand, I'm worried about this. Remember all of that stuff that came out of the Hellas Impact Basin, all that big cratering? If you took all of the ejecta from all of the craters that have blasted in the planet, and you took all of the different volcanic flows and all the other things, the sedimentary deposits and whatnot, and layered the planet evenly, which it isn't, but let's say we did, in essence what you would have is 2 kilometers of that. What that is right there is a picture of the Mars Pathfinder site, and these are like blocks of basalt. What, 30, 40,000, 50,000 psi compressive strength? And it's surrounded by dust, dirt, unconsolidated. Now I know, I've worked with lots of people from all over the world, and it doesn't matter. When you talk to a drilling engineer, wherever they work is the hardest drilling on the planet. It doesn't matter. You know, it's always the hardest, right? Just ask any driller, they're always going to say, yeah, well, we work the hardest place. So I'm here to tell you, I think this is worse. You know why? Think about it. You've got to have a drill bit that can go through an ultra-hard basaltic type of rock and then be able to control and be able to drill through dust for 2 kilometers. Talk about a bit design problem. So that, I think, is pretty bad. Now, back in May of last year, we had at the Goddard Space Flight Center a planetary drilling workshop. You know, you got to admit, that's a pretty cool title. And so what we did is we had a bunch of scientists that are interested in the looking and drilling on other worlds. We had us academic types. And we also had, believe it or not, Halliburton. We had National Oilwell Varco. We had Atlas Copco. And we had Baker Hughes there. And they were all represented by their fine folks that came to that meeting also. And it was very fascinating listening to the give and take between the scientific community and the oil field people. Because I think both groups have something to share. And so one of the things that we did, though, is like, you know, as we want, we just sort of classified drills. And so we came up with a classification scheme for extraterrestrial drills. We have what we call, yes, the 10 centimeter class drill. 10 centimeter class drill. So there's the first type of drill. And I mention that because that turns out to be the state of the art. The next generation of drills will be what we call the 1 meter class drill. That is, think of it as just like one single stand of drilling, like 1 meter, maybe 2 meters, that you can drill with. You don't have to screw pipe together because a 10 meter class, I got to screw pipe together. Why? Try to put a 10 meter pole inside of a spacecraft. And so you have to screw that together. And so the order of magnitude of difficulty of pulling that off without having problems is what I would call the next generation. And then finally, the holy grail is the really deep stuff. Yes, 10 meters or more. The very first project I was asked to do with NASA was to look at the feasibility of drilling a 10-kilometer hole. Yes, 10 kilometers. And what I found fascinating was what they were wanting me to drill it with. Oh, I didn't bring it. I was going to say, I have a pen. That's the diameter, a pen, like a writing pencil. That was the diameter they wanted to drill. I actually had a drill bit that I was testing, and I managed to break it within 30 seconds. And so all I can say is this: don't let aeronautical engineers design drill bits. Speaking, though, of that, they did come up with a really clever thought, and that is, you know, one of the things that the scientific community does, and the engineers, especially at JPL and so forth, have done is they kind of boil drilling down into its absolute minimum, you know, because you can't just launch everything. And so they said, okay, what does it really take to drill a hole in the ground? And I thought that was a very useful thing, because when you think about it, everything on a drilling rig is to do one or more of these 3 things. 1, it's got to penetrate the rock. 2, you've got to remove that rock. And 3, you have to support that borehole. Think about it. Every drilling rig, when you construct a wellbore, has to penetrate the rock, remove that rock, and support that borehole. That's in essence what's going on with drilling. And if you boil it down to the absolute minimum, that's what we do. Now granted, there's a lot of other stuff around it, but if you think about it, everything has got something to do with one or more of those 3 things. Now when we talk about penetration, one of the key things there, and this is something we're seeing in industry today, and that's energetics. How much energy, specific energy, is how much energy does it take to remove a unit volume of rock? The closer you are to the minimum, which is typically considered to be about the compressive strength of the rock, the more efficient you drill. It's called mechanical specific energy. And it turns out one of the most efficient ways to drill energetically is mechanically breaking the rock, better known as percussive and rotary. Why do you think so many rigs are all percussive and rotary, and why things like lasers haven't taken off, or thermal spallation hasn't taken off, or chemical dissolution isn't taken off? It's the energetics. It's much more efficient to drill with a mechanical device. Now, what about the cuttings transport, being able to remove the rock? I can only think of 2 ways to do that. You either mechanically auger it out, or you pump a fluid, and the fluid carries it out. What do we use today? Of course, the drilling fluid. You know, you probably heard it called mud. And so that's what we use, in essence, to be able to remove those cuttings out of the hole. But an auger could work too, but the problem with an auger is as you get deeper, the friction on the sides of the hole gets so high that it just basically screws itself into the ground. And so that becomes a real interesting challenge. How about borehole stability? Well, of course, we got drilling fluids, right? They put a little hydrostatic pressure on the system. But as I tell my students, if you want to cure a drilling problem, line it with steel. Run casing, right? Run casing. You can really get a really good, nice and stable borehole when you got steel lining it up. Now, that's what drilling's all about. But what about spacecraft? When it comes to spacecraft design, you got mass, volume, and power problems. Mass, because I've got to accelerate like a kilogram of mass to 11,500 meters per second. That takes a lot of energy. Another way to say that is it takes a lot of money, right? Rocket ship, get it to go that fast, just to get it out of the Earth's gravitational field. You know, even a tenth of a kilogram is expensive. How about the volume? Think about the nose cone on a rocket ship, right? When you think about the nose cone on a rocket ship, there's just not a lot of room under that parabola. And so therefore, you've got to fit everything in there. It's like a little origami thing that they got to be able to put all their spacecraft together inside the nose cone of a rocket. And then power. The Viking and the Curiosity are powered by nuclear radiogenic thermal devices. Nuclear power. The Opportunity, Spirit, and Pathfinder were solar panel powered. And when you think about it, 50% further from the sun, inverse square law, you just don't get a lot of power from that. So if you get 5 or 50 watt hours out of it, that's pretty good. But even with a nuclear power source, 2,400 watt hours is pretty darn good too. In other words, you're really severely limited in energy. Of course, we have had some extraterrestrial drillers, the lunar astronauts. They drilled about 9 meters worth of core on the moon. They had a 500 watt battery powered human operated device that they kind of pushed down. And in fact, when Dave Scott tried to pull it back up, he managed to wrench his shoulder. So it was almost the first lost time injury on another world. I understand he just sort of hushed it up because he didn't want to have NASA tell him to get back in his spacecraft and go home. So you think you've worked in some isolated places? These guys have worked in some really isolated places. So what are some of the current ideas in drilling exploration? Right now we've got what we call the RAT. The RAT is on Mars. And we also have the RASP, as well as some various robotic tests. And I do want to mention about the lunar drill that's being developed for the Google X Prize. The RASP is the rock abrasion tool. Remember on the Opportunity and Spirit, I pointed out that little arm? What that is a little device that sits right here. It's got a wheel that, as it rotates, it's got a little diamond incrustation on it, and it just sort of cleans the rock off. They pull it back, do a little microscopic image on that. What's kind of interesting is that this little shield right here is actually from the World Trade Center, because the company that built this is in Manhattan, New York, during that time of the World Trade Center disaster. The scoop from the Phoenix is another device. It's just no more than very similar to what you might use on a backhoe. And one of the things about Mars is it's always surprising us. They went down and scooped up some of the soil right off of the ice, dropped it into the onboard laboratory, and it had 150 micron mesh screen on there. And they expected it to be dry and the soil would just go right through it. It did not. It clumped up and actually just sort of wadded up on top of it. It's just like plump, and then that was it. Mars is always surprising us with its chemistry. And in this case, it didn't quite work. They got enough to say, though, that indeed that was water ice. The Curiosity has its own little drill. And actually, this is that other boom I was mentioning on the Curiosity. It's actually a drill system that is got 20 kilogram weight or mass on it, and it's 100 watts, and it basically generates powder. And I'll mention that powder in just a minute. But it sits there and it drills into the rock or whatever. And in fact, they've already done it back in February of last year. This is the first hole on Mars. It is a grand total of 6.4 centimeters deep and 1.6 centimeters in diameter. And it generated all this powder, which happens to be a form of clay. Not satisfied. Of course, they always want to go for records, and so this is the record hole on Mars. It's the Cumberland site, and it is a grand total of 6.6 centimeters deep. This is the deepest hole on Mars. All right? And again, you notice the powder and all that. I mentioned the powder because it turns out the drill bit is a solid impreg diamond bit. And what those do is they have a tendency to generate powder, which means that from an energetic standpoint, because you're breaking the rock up into smaller and smaller and smaller pieces, the powder, it's not very energetically efficient. So that's just a little aside. Now, when we go to another world, we're going to have to do some testing. And what I find interesting is you think about all the things that goes on. For example, how do you know the sample you got is correct, that it's not some sort of weird thing going on? Well, that was what the MARTI was all about. It's an astrobiological research technology experiment to be able to test if you could take samples without goofing it up. Can you actually take a sample from here and not cross-contaminate a sample from there? How do you know that sample is right? Of course, the area I'm interested in was the DAME, the Drilling Automation for Mars Exploration. Not many rig crews on Mars, and so therefore everything's going to have to be automated. And so the idea was, can we create some automation routines to be able to run a rig on another world? What I find fascinating about this is those of you that may have gone to the Dallas SPE annual conference, I believe it was in 2006. If you went to the east side of the exhibit hall, guess what was sitting there? Yes, that thing was sitting there. And they actually had a little exhibit of that particular device. I mentioned this one right here because even though it's not have to do with Mars, it does have to do with the moon. It's a teleoperated system. This is Dr. Chris Zagney with Honeybee Robotics. He helped me a lot with putting this presentation together. And he created this little rotary percussive type drill system right here and was able to teleoperate it by a 6th grade class in California while he's sitting here in Antarctica. And what's really neat is that they got a meter an hour with only 100 newtons weight on bit and 100 watts. I think that's an amazing achievement to be able to pull that off. Now, I mentioned earlier about some of the stuff coming up. Well, the NASA InSight mission is getting ready to launch in 2016, and it is a geophysical study of the planet. They're looking for the seismicity on it, they're looking for the heat flux coming out of the planet and so forth, and it's got this rather convoluted acronym to be able to come up with the word InSight. But the one I'm interested in is the HP3. It's a percussive drill system. If you look right here, see that little device that kind of lays out and come out? It's actually got about a 40 centimeter long spike that inside of it has a shuttle. It's about 3 or 4 centimeters in diameter. And as this shuttle vibrates, the idea is this kind of hammer its way down, and it wants to go down about 5 meters. It's got a little tape that comes out of this box that keeps the power going to it, and it's just going to drag that whole thing down so that they get a really nice seismic connection to the planet, as well as to be able to get the idea of whatever the heat flux is coming out of the planet. This is being developed by a German company, so it's very interesting to see if they can actually pull that off. Of course, the European Union has also got an opportunity here, and that is the ESA ExoMars drill system planned for 2018. It's a 2-meter class type of drill, and it will collect 17 of these 1 centimeter by 3 centimeter core, retrieves them, puts them to a lab, and what I really find fascinating about it is that it has a multispectral infrared imager on the drill string. In other words, the first interplanetary LWD. So I find that very fascinating they're going to do that. Of course, the United States said, we did really good with the Curiosity, got that thing landed, but driving around with it. Let's do it again. So they proposed the Mars 2020. What's really interesting about it is it's going to be the same chassis and the same the way they landed it on the planet, but they want to put a bigger drill on it. And rather than take a drill and put it on an onboard lab, they want to just take these little core samples, put it into this little chamber right here, and then set the chamber over. And then sometime in the 2020s, send another rocket down there, go and grab the chamber, put it on the rocket, and ship it back home. So who knows, maybe in the next decade, we'll have a whole bunch of samples of Mars coming to Earth. Of course, this is what they really wanted, and that was the deep drilling mission. That was the 10 kilometer. They want to get as deep as they can. Why? Because they don't know where the water table is. And so that was the idea. And so this is just some sort of scientific, I call it a liberal arts version of what a deep driller might look like on another world. So how does this help us? I mean, that's the point of what I'm trying to get across here. If you notice, I said at the very beginning, we wanted to find the answer. Is there life elsewhere? Are we alone in the universe? And how does that have anything to do with us? I think I've already pointed that out. That basically what we're doing is we're finding resources underground. Isn't that what we do for a living? And so when you think about it, the technology development to be able to create a machine that can do that. Well, for example, understanding drilling mechanics. I'm a drilling engineer, right? I need to understand energetics. I need to understand how to apply energy to efficiently break the rock so I can drill faster, I can drill deeper, and I can drill cheaper. And so understanding that how the rocks actually break, how do they behave? And if I understand that, I can do much better here on Earth. How about sensor technology? Don't we, as petroleum engineers, actually find ancient life every time we drill, or at least we hope we do? Isn't that better known as oil, gas? Aren't they hydrocarbons? Aren't they remains of life? Isn't that what we're doing, is finding ancient life? The answer is yes, you bet. And in fact, hydrocarbon detection is one of the key things of being able to find life. So think about it. If we were, in the Rocky Mountains where I'm from, we're drilling these Niobrara wells. One of the things we're looking for is total organic carbon of those shales. The higher it is, the more juicy it is. We're looking for life. How about drilling automation? I think the next great thing in drilling rigs is drilling automation. Get people off the rig floor, keeps them safe. Be able to make it more efficient operation, be able to have it more consistent. So understanding the routine stuff, being able to do things. I'm part of the Drilling Systems Automation Technology section of the Society of Petroleum Engineers. One of the things they're trying to do is what they call drill a stand. In essence, create all the algorithms necessary to be able to drill one stand on a top drive type of rig. That's actually quite a challenge because you also have to consider what happens if something goes wrong. What if some poor guy's got his hand in the wrong place? Does the machine know enough for the non-routine stuff to shut down and go, nope, we're not going to do it? In fact, trouble avoidance and recovery is a very important part of any sort of automation. I really wish the people at the Gulf oil spill had some sort of device on board that would have warned them that they had more coming out than they had going in. How about the testing procedures and equipment? When you think about it, the oil field has stuff that is far beyond anything the military or the aviation industry or any of those other folks that have this high-tech stuff. Well, we beat them all. We've got high pressure, we've got high temperature, we've got corrosive environments, we've got shock loading that just puts everybody else to shame. The devices that we build are amazing. And testing it to make sure it does what it's supposed to do is a useful thing. I think about building specialized equipment. The X-15 is a rocket ship that was developed by NASA back in the 60s. Fairly worthless, when you think about it. All it did was go really high and really fast with one guy for about 5 minutes. But what we learned about aeronautics from that allowed me to fly from Denver to here in comfort. How about an X1 or the Formula One cars? Formula One cars, can you imagine driving a Formula One car out here? Really lousy, right? But what we learned from the suspension, the engine, the safety, the fuels, allows us to drive routinely around the world. I think of it as extreme machines for extreme environments. If we build an extreme machine for an extreme environment, we learn about how to do it better here. And that's how on Earth it can help us. So in conclusion, there's a lot of challenges we're going to have to overcome. Things like drill system autonomy, all the different aspects of that, as well as the power, volume, and mass to be able to launch something to another world. And how about the autonomous sampling and so forth? Can we sample stuff and be able to know and have an answer? Is there life elsewhere? Solving those issues there will help us better understand what we're doing here and to be able to solve a lot of our own earthbound problems and all that. You know, another thing that I think too, it generates excitement. Our industry is literally on the leading edge of trying to answer the question that has vexed mankind for a long time. Are we alone in the universe? And our industry is going to be the folks that are going to do it. I don't know when we're going to Mars or the moon or wherever we're going, but I do know this. When we get there, I will bet you there will be a petroleum engineer on board. And in fact, it'll be a drilling engineer. Let's hope this guy's not his driller. And with that, I thank you very much, and I would be delighted to answer whatever questions I can.